Is it there? Okay, so let's get started. We have today we're going to talk about rational functions and how rational functions behave. So we're going to kind of go through the same drill that we did with polynomial functions and compare them to the toolkit functions to see, can we predict the behavior, and if we can, specifically what happens. Now, a rational function involves ratios of two polynomial functions. So if P and Q are polynomial functions, we'll take the ratio of those and call those rational. Now, when you use the word rational in math, you're not talking about rational as sane and irrational as crazy, like you say, an irrational person. It's not rational in that sense. It's rational in the sense that it comes from the word ratio, and so we have a ratio of two polynomials. So an example would be something like our toolkit function 1 over x, right? 1 is a polynomial, in a sense. X is a polynomial with one term. And so we look at the way this thing is, its long-term behavior as x goes to 0 from the negative side. That means it's coming up this way. The function is going to go to negative infinity. That means the closer we get to 0, the more or the smaller the function is going to be. Then if we look at the other direction, as we get close to 0, as we're coming from infinity to 0, it's going to get increasingly large. Now we look at the long-term behavior. As we go out to infinity, the function gets closer and closer to 0. And when we go the opposite direction, it gets closer and closer to 0, although it comes from the opposite direction, from the negative side. Okay, so this is a key thing to remember about 1 over x. Now the thing to compare it to is 1 over x squared. Now 1 over x squared looks like this. Okay, so the general behavior is about the same, except on the negative side. So as we go to 0 from either direction, the function goes up to infinity, and as we go to either positive or negative infinity, the function goes to 0. So notice everything is positive here, while this one, the 1 over x, if we have x equals negative 10, it retains the negative, so we have negative 1/10. Here, if we have x equals 10, we have 1 over 100. Or if x is negative 10, yeah, it'd still be positive, 1 over 100. Okay. Everybody got that? So that's just kind of where we came from with the toolkits now. Now I want to introduce two words here that we're going, or two different things that we're going to deal with a lot with rational functions, are asymptotes. Okay, and I'll spell this on the next slide, but asymptotes are these boundaries where it doesn't cross over. So as x gets closer and closer to 0, it doesn't go over x, it just basically gets closer and closer to x. Same thing as it goes closer and closer to 0, it gets closer and closer to the y-axis, but never crosses it. So here we have an asymptote. So if we look at this function, the toolkit function, and we're going to add 2 to it, what happens? We're going to raise the function up by 2 units, right? So this thing is going to look now, instead of things leveling out at 0, it's going to level out at 2. And so we call this a horizontal asymptote. So what we didn't see with 1 over x is that the asymptote was the x-axis. And now, since we've added 2 to the function, it raises the asymptote to be x equals 2. And so we're going to use dashed lines to represent asymptotes. Now, let me make this substitution. 1 over x plus 2 is the same thing if I make a common denominator, 2x over x, and so I get 1 plus 2x over x. So here's my function. So this is a rational function. This may not look like a rational function to you, like this, but in this form it is a rational function, a polynomial over a polynomial. And it behaves like 1 over x. So one of the things I want you to notice is look at the leading terms of the polynomials. This is going to be one of the key indicators that you have about how these things perform. Notice the asymptote is 2, or notice the ratio of the leading terms on both, 2x over x. If you simplify it, it's 2. And so if both of the numerator and the denominator have the same degree, that ratio is just going to be the ratio of the leading coefficients, which in turn will be your horizontal asymptote. Now, one of the things to remember is you only ever have one horizontal asymptote, okay? So let's look at this function now, where we have f at x minus 2. So what are we going to expect? That this thing is going to move over to the right 2 units, right? When f at x is 1 over x. And so if I plot this out, my vertical asymptote is going to move from the y-axis over to x equals 2. And so if we work out what the function is, we just have 1 over x minus 2. Now notice that the denominator has a higher degree than the numerator. And that's a sign that we're always going to level out to 0. So as x increases, the denominator is always going to be bigger than the numerator. So as we go to infinity, that means that this is going to go to 0. Okay. Everybody okay here? Now I've said a lot. I'm going to be repeating a lot of these characteristics. But the main thing that I want you to get is that we have our same basic function, and by either adding 2 to the function or adding or subtracting 2 from x, these things are moving around. And then we're really going to be representing them mostly in the rational form. And sorry, I know some of you are bobbing back and forth to see the bottom. I can't raise the screen very much, or actually at all. Okay, so let's keep on going here. So let's look back at horizontal asymptotes. Take a closer look at that. So with our rational function, being the ratio, the horizontal asymptote is determined by the degrees of the polynomial in the numerator and the denominator, and we only have one horizontal asymptote ever. Okay, it's not possible for us to have 2. So if the numerator is higher, like this, if we have a 3x7 and 2x to the 4th, remember that the long-term behavior of the polynomial is going to look like the leading term. And so this is going to be 3x to the 7th over 2x to the 4th, which is what you would expect its long-term behavior. If you do the division then, it's 3/2 x cubed. So how does x cubed behave? Well, it goes off to infinity as x gets larger. So here's the long-term behavior. The leading terms, it's going to behave like this long-term, both when x is very negative and very positive. So no asymptotes here because it's going to go off to infinity. If the denominator degree is higher, then as x goes to infinity, the function goes to 0, because with a higher, think about, let me see if I have an example here. I don't have an example. I'll write one here. If we have, let's say my g at x is going to be the reciprocal of f at x. Let's say that's 2x to the 4th minus x cubed plus 1 over 3x to the 7th plus x squared minus 1. Remember, the long-term behavior is going to be like the long-term behavior of the leading terms of these. So the long-term behavior of this thing is going to be approximately 2x to the 4th over 3x to the 7th, which if I simplify that, that's going to be, whoops, this is 2/3 x cubed. The long-term behavior of this, as x goes to infinity, either positive or negative, this thing is going to get closer and closer to 0. So the long-term behavior when the degree is higher in the denominator is that the function's going to go to 0. So in other words, your horizontal asymptote is going to be 0 at that point. So if the degrees are the same, then the horizontal asymptote is the ratio of the leading coefficients. And so if I make my function h at x equals, let's say, 3x to the 7th plus 1 over 3x to the 7th plus x squared minus 1, if I approximate my long-term behavior as the leading terms, 3x to the 7th over 3x to the 7th, this is going to be equal to 1. And so my horizontal asymptote in this case is maybe if I make this a different example, I'll make this 4/3. 4/3. Then my horizontal asymptote is going to be the coefficients, okay? So the three cases to remember. Higher degree, it goes off to however that the difference of the degrees go, and you know how that happens. If the denominator has the higher degree, that means as x increases either to a very large positive number or a very large magnitude negative number, it's going to go to 0. And if they're the same degree, then the horizontal asymptote is going to be the ratio of the leading coefficients. Okay, so those are the three things to remember. And so here's the example, 6x cubed plus other things over 2x cubed plus other things approximates 6x cubed over 2x cubed, so the x cubes cancel out, and so my horizontal asymptote is going to be 3. Yes?
So if the denominator is higher than the horizontal asymptote would be 0?
Yeah, the long-term behavior, it's going to go to 0, and so you have a horizontal asymptote of 0. Now notice with ratios of polynomials, the only way that you're going to actually cross 0 is if the numerator polynomial becomes 0, and so if it's the higher one, it's perfectly fine for the graph to cross 0. If it's the lower one, then it's going to ultimately, go to 0, but you might have a point where one single point where it goes through. Okay, so let's look at vertical asymptotes now and how they arise. Okay, so these arise because of the denominator exclusively. Okay, so when the denominator equals 0, our function is undefined, right? The roots of the polynomial q tell us where f at x is not defined, so the values that make that happen are outside of the domain of f. So, for example, if we have, let's say, this polynomial, where x equals 1, x equals -2, and x equals 3, that'll make this all 0. So we have to say that these asymptotes exist here because the asymptotes will show you are single values that are outside of the domain of the function. Just like 1 over x. If we remember what 1 over x looks like, it's like this. X cannot equal 0, and so what happens is as you get closer and closer to x, you get a bigger and bigger number from the positive side, like, right, when you get, if this is 1 and you're at 1/1,000th, you take the reciprocal of 1/1,000th and you get 1,000,000, you're way up there. The closer you get to 0, the bigger it gets, but you can never be at 0. 1 over 0 is not defined. Okay, so your vertical asymptotes come from the roots of the denominator's polynomial. So here we're dealing with short-term behavior, which are around the roots. If we have 1 over x it's going to, or an odd number, it's going to alternate like this. So in other words, when we come from the negative side closer to 0, it retains the negative. So if we're at negative 1/1,000th, when we take the reciprocal, we'll be at negative 1,000,000. Okay, when we come from the positive side and we're at 1/1,000,000th, then it goes up to 1,000,000. So it alternates because you have the alternate, or you have the odd degree. So 1 over x is your prototype odd degree reciprocal. So that means the direction alternates on how you go to infinity next to your asymptote. Now, with 1 over x squared, remember that looks like this. Whether we're negative or positive, x squared makes it positive, so either side goes up to infinity. And so with even-numbered exponents in the denominator, we're going to go to infinity and come back from infinity in the same direction. Okay, and intercepts, you know how to do intercepts. Intercepts are when the numerator equals 0. Denominator are your asymptotes. The numerator will tell you your x-intercepts. Evaluate f at 0 and you'll get your y-intercept. Okay? So when f at 0 is your y-intercept, when p at x equals 0, those are perfectly good numbers. It's just when it crosses the x-axis, that's how you find your intercepts. Okay, so occasionally we'll have holes in the function. And what I mean by that is we have something like this, where this is, we have every number here except one particular number. And the way we get holes is that we have a domain restriction that we can eliminate. And so if I show you an example, perhaps this will be more clear. If I have this, okay, this simplifies by canceling out those two terms into 1 over x minus 1. But remember that you have to restrict the domain here where x can't equal negative 1. Even though that's a perfectly good number, negative 1 minus 1 is going to be negative 2. It's actually going to have a hole because your function is not defined there. So however this thing graphs, when you get to negative 1, you have to put a hole because you've restricted the domain where the domain had a restriction before you simplified it. So the simplified function looks exactly like the original function everywhere else, but we have to, in order for this to actually be the function, we have to restrict the domain because it turns out that in the original function, it couldn't equal negative 1. So in this case, if I graph this, this is what 1 over x minus 1 looks like, right? We have the asymptote at 1 because that's going to be the root of the denominator. It's going to alternate because we have an odd power on there. But what we have to do is we have to eliminate negative 1 because negative 1 doesn't work in the original function. So if you had me in Math 12, I think there's only 2 or 3 of you that have had me in Math 12. One of the reasons why I was so fussy about grading these things when you're simplifying polynomials is because it becomes very important at this point to remember the domain restrictions. Yes?
Why is it just negative 1?
Well, that's the only thing where it's not defined. I mean, here, when x equals 1, we have our asymptote. So that's outside of the domain too. So if we looked at the domain of this overall function, that's all real numbers except negative 1 and 1. But they look different on the graph. The ones that we can eliminate by canceling them out are holes. We still have the nice smooth line before and after it. But the ones that we don't cancel out actually become asymptotes. Because if we get really close to negative 1 here, no matter how close we are, if this is a billion over a billion or a billionth over a billionth different, you know, it's still 1. this one changes independently, and so this forms that asymptote that actually drives it to infinity or negative infinity. Okay, have I thrown enough rules at you yet?
Is the lecture going to be online like the video?
Yeah, we're recording this, and hopefully I won't push the stop button inadvertently like I did last time. Okay, so let's sketch this graph. Now I'm going to do a few examples, and hopefully this will clear up some of those things. What you're going to have to do with these is that you're going to have to go through and say, okay, what do I know about rational functions? Okay, you know how to find the intercepts. You know what causes asymptotes, both horizontal and vertical asymptotes, and you know your basic toolkit functions to know what direction things are going. Okay, so let's look at this one. We have the numerator and the denominator. The degrees are the same. Now, you don't have to multiply these out to figure that out. You just look, this is an x squared, right? Because your highest degree is going to be the leading two terms here. And this is going to be an x squared in the numerator. So the degree is the same between the numerator and the denominator. And so the ratio of the coefficients, we have a horizontal asymptote at y equals 2. So that's the first thing we can get out of this just by inspection. Same degree, numerator and denominator, what's the ratio of the leading coefficients? Now, vertical asymptotes, we know we're going to have two of them because we have two places where we can start dividing by 0. One of them is where x equals 1. The other one is where x equals negative 2. Now, the y-intercept is easy to calculate. We just plug in a 0, and so we get 2 times 1 times negative 2. So I'm just putting zeros in there. And so I get 2 times negative 2 over negative 1 times 2. And so my y-intercept is at 2. And my x-intercepts I get because I look at my numerator and say, okay, at x equals negative 1 and x equals 2 is where I'm going to cross the x-axis. Okay, so I got lots of information here. So let me start sketching it out. Okay, so because this is kind of compressed, I'm not putting the numbers, but when you're sketching graphs, I would like you to label your axes because you might occasionally make this 2, 4, 6, 8 rather than just 1. But here I have my horizontal asymptote at y equals 2. I have my vertical asymptotes at x equals 1 and x equals negative 2. And then I'm going to plot my roots here, or my intercepts, at negative 1, 2, and 2. Okay? So now the question is how do the lines connect now? How does this all work out? The asymptotes are fences. They're boundaries. You can't cross them with your polynomial. So what you start thinking about is, what's the long-term behavior of this? Like, in other words, when x is really, in the words of Donald Trump, huge, okay, what will this be? Well, this is going to be a positive number, right? So we know it's going to be above the line. Is it going to be more or less than this number? That's harder to tell, right? So we know we're going to be around here, but where is it going to come by? Well, we know when x equals 2, it's going to go through here. And we know it's going to have this kind of a shape, right, because we don't have any squared terms in there. So it's going to be reasonable for us to assume that this thing is going to go down like this, okay? Now, if it goes down like this, around this asymptote, this is x minus 1 is causing that asymptote. I don't have a squared on here, so I'm going to expect that it's going to come from the other direction on the other side of this asymptote. And then it's going to go through this, it's going to go through that, and then it's going to go down like this. And you think, okay, how do I know it's going to go down like that? What we can do is think, okay, as x is going to negative 2 from the positive side, that means I'm going down this way. So the positive side means I'm coming from numbers that are bigger than negative 2. What happens? I can look at my function like this. And remember those exercises of making the tables of pluses and minuses? Just make the table for 1. So when this is just under negative 2, this is going to be negative. So when this is or just above negative 2. When this is just above negative 2, this is going to be negative, right? Because if it's like negative 1.9, it's still going to be negative. When this, if this is like negative 1.9, that's going to be negative here too. And this one here is going to be positive. So if I tally all these up, it's going to be positive over a negative. This thing is going to go negative. So the closer I get to negative 2 from this side, the more negative I'm going to get. Okay, and that's just because I've tested something on this side of the line. Now with this rule of alternating, I'm going to then have a part of the curve that's up here like this. So let me draw that in. And I'll explain my notes. What happens? Okay, so as I get close to 1 from the positive side, my first factor is positive. My second factor, really close to 1, is actually negative. These two factors, when I'm just a bit over 1, are going to be positive. So you can see that this thing goes to negative infinity as I'm getting closer and closer to this. So I just assess what's the sign of this thing, and I know that as I get closer and closer to 1 from this direction, I'm getting more, I'm getting a bigger and bigger magnitude number, but it's going to be negative. Now, if I go to 1 from the negative side, when I'm going through here, look what changes. All of these are the same except this one here. When I'm just slightly below 1, this is going to be negative. When I'm slightly above 1, this is positive. And so that's what changes here. And then, you know, this whole thing works out to be positive, so it's coming down from the positive side. Now, as we go to negative 2 from the negative side, so that means we're coming up from this way, we're going to see that all of these things are going to be negatives, and we have an even number of them, so that it's going to go up to positive infinity. And so there we go. And we can make a similar argument for this one. But oftentimes, all you need to do is 1 or 2 of them, because if you know that you don't have any squareds in here, you're coming and going from different directions. Okay, so once you get one direction right, you just alternate it for the other one. It's okay to check yourself, but you know you can generally get away with just doing this once or twice rather than a potential 4 times here. Yeah.
I'm sure you've already answered this. I thought you couldn't cross the horizontal asymptote.
In the long run. Short term you can. Okay, so it's just, this thing is not going to wiggle above and below in the asymptote, and it's not going to do the same thing here. It's not going to cross here. But in the short run where you're close to your roots, it can. But that's a really good question, a good point. It's not a boundary that says, oh, I have to turn around because I can't cross that. So it's true for the horizontal one, or the vertical ones you never cross. The horizontal ones you don't cross in the long run.
Unless you're in between two.
Yeah, just in between, you're fine. And in fact, something like this, you're actually on the asymptote, right? You're the intercept. Okay. So another example here. So we have x plus 3 over x squared plus 1 squared x minus 2. So let's look at the long-term behavior. The degree in the denominator is larger than the degree in the numerator. So for my long-term behavior, I know that as x goes to infinity, I'm going to go to 0. And as x goes to negative infinity, I'm going to go to 0 as well. So that's what the higher degree tells you, your long-term behavior. So in other words, your horizontal asymptote is y equals 0. Okay, so let's look at our vertical asymptotes. Vertical asymptotes happen when our denominator has a 0 factor in it. So we have a -1 and we have a 2. So there's our vertical asymptotes. Now the y-intercept we get just by making x equals 0. And so if I make x equals 0, what I have is 3 over 1 times -2, and so I get -3 halves. I only have one place where the numerator can get to 0, and that's where x equals -3, so there's my x-intercept. So I have 2 intercepts. The y-intercept at -3 halves, the x-intercept at x equals 3. Okay, so this is about what I have to to work this now. Horizontal asymptote isn't shown because it's the axes. All right, now let's think about how we're going to, well, first let's plot the roots, okay? And so here I have two roots, one here and one there. Now this one is on 0, and that's okay. Our long run behavior says it's going to be 0, and it's not going to be at 0 the whole time, but we can still cross the asymptote because we're close to, we're into short-term behavior here. Here's one that really kind of gives us a clue though. But anyway, so we go through and we say, all right, let's come from the top here. As x goes to 2, as we're decreasing x, so x is just a little bit above 2. When it's a little bit above 2, this is going to be a positive factor. When this is a little bit above 2, this is always going to be positive because it's squared. And when we're a little bit above 2 here, we're going to be positive. So all positives, so this is going to go to infinity. So we know that our first point goes from 0 up like this. So it looks a lot like the 1 over x toolkit function on the right side. Okay, so I guess I did all these things first. So if I'm going to come to 2 from the negative side, that's this direction, I know that this is still, it would be a little bit below 5, but it's still going to be positive. This is still going to be positive. But if I'm a little bit below 2, this is now negative, right? If I'm at 1.99, this is going to be at negative 0.01. So I'm going to be negative. So as I go this way, it's going to go negative. All right, so it's going to go down this way. Now the next one I'm going to do is I'm going to go to 1. So I'm coming to negative 1 from this direction. The numerator is going to be positive. The denominator is going to be positive, right? Because I'm going to be just a little bit of, this is going to still be a positive number regardless of what number it is. This one here, as I go to negative 1, is going to be negative. So I'm going to go to negative infinity. So this thing is going to come up here, and then it's going to turn around. It's going to go through this point and go down to negative infinity. Okay, and then if I go to negative 1 from the left side, this is still positive, okay? This is always positive, and this is going to be negative as well, so this is going to be negative. So when I sketch in my, my graph, this is what's going to happen. Now this is a little odd because I'm going to go through the axis, but then I'm going to start leveling out and return back to y equals 0. And notice that here I'm going and coming in the same direction, and that's where x equals negative 1, and look at that. That's where that squared comes in. Okay, so this one, because it doesn't have a 2, I'm alternating. This one, because I do have an even exponent, means I'm returning from the same direction I went to. Okay? All right, let's do it the other way around. Let's now, actually no, this is, what I did was I plotted this on a plotting program. This line, that's the asymptote, is just what happens with this graphing program when you go from positive infinity to negative infinity. But there I have the basic shape that I came up with before. I didn't go out to negative 3, but it touches it and then goes above it and then it declines again. Okay. So now let's make the equations from the graph. Okay, so I have several things going here. I have one x-intercept at 2, 0. I have one y-intercept at 0, 2. And I have two asymptotes at negative 1 and 1. And then my long-run behavior is going to 0, okay? So what do I know about this now? Well, I can set up my, so the long-run behavior says that the denominator has a higher degree than the numerator. Now my vertical asymptotes, as being 1 and negative 1, means I have well, I have what I have, and then with my root of at 0, or f at 2 equals 0, that implies that I have this in the numerator, x minus 2 in the numerator. And so I can build up my function like this. These two come from the fact that I have my vertical asymptote. This comes from the fact that my intercept is at x minus 2. And notice my degree is 1 on the numerator, 2 on the denominator, so that's consistent with my long-run behavior expectation that when it's 0, the denominator degree is higher than the numerator degree. So the only thing that remains now is what is A? Okay, we have some sort of coefficient here, and so we're going to use the y-intercept to determine A. And so I'm going to say, okay, f at 0 equals 2, and so when I put zeros all through here, I get 2 equals 2a, and so a equals 1, and so here's my function right there. So think back to graphing polynomials. Pretty straightforward, huh? Compared to this, right? Okay, everybody up with me here? Okay, I'll give you another minute or so.
So do we have a test like Wednesday?
Yeah. At the beginning of class, I said that I posted some review questions, and you'll see 2 questions that pertain to this stuff. Okay, so let me go on. All right. Why don't you try and come up with the function that is like this. I have a horizontal asymptote at -2. Think about where that comes from. That comes from, and I'll tell you right now, it comes from the fact that the degree in the numerator and the denominator is the same, and the ratio of the leading coefficients is -2. Okay, we have 2 vertical asymptotes, which means we have a factor of x plus 2 and x minus 3 in the denominator. We are coming and going from the same direction here, but in opposite directions here. So one of them has a degree of 1, and the other one is a squared 1. And then what we have here is an asymptote, or an intercept. Our only intercept is 0, 0. Okay, so have at it with that one. So the first thing that we know, we have this x plus 2 because of this, and we have the x minus 3 because of those asymptotes, right? And we also know that the numerator degree now is a 3rd degree. It has to be, right? Because we're going to have an asymptote that's not 0, so we have to have the 3rd degree numerator to match the 3rd degree denominator, so we can take a ratio of coefficients. Yes?
How do you know that it's squared for the x plus 2?
Because it comes and goes at the same place. Okay? And this one goes opposite. And you let when we put that a up here, we're going to let that take care of, are they both above or both below? You know, they'll alternate like this, and it will work out. Okay, so we're looking for a 3rd degree here. So the ratio of the leading coefficients is going to be -2, right? If all of these factors are just x without having anything in front of them. So if this is x something, we're going to have a -2. So how do we do this now? We only have one root. Anybody have any idea? There's a clue up here that tells you something. Yes?
I just have a question. How do you know that x plus 2 is squared?
Because the way it goes on the asymptote, it comes and it goes from the same side.
What?
Remember?
I don't get it.
With this, 1 over x squared, these, they come and they go from the same side. This comes and goes from the opposite side where we have an odd number here.
But how do you know it's x plus 2 rather than x minus 3?
Well, this is at the asymptote's at x minus 2, so the factor here is x plus 2. That makes it in the denominator, which makes this asymptote. So if I just looked at the asymptote alone, I know I have this in the denominator. Okay? So when I look at the behavior of the function on either side of it, it comes and it goes to the same place, so that has to be even, and we're going to just limit it to 2.
Okay.
Okay? And then this one comes and goes in opposite directions, so x minus 3, when we have x equals 3, we get division by 0, and that's why we have the asymptote. So that's going to be a 1 because it comes from the opposite side. Now look at the behavior around here. Remember with our polynomial functions when we had a root? It goes straight through when we have a single root, but if we have a multiplicity of roots, it levels out. It either goes the other direction or it goes in it continues in the same direction after it flattens out when you have a higher degree. So one of the things that we know now is that we have an x here, because when x equals 0, we know that f at 0 equals 0. Okay. But we have to make the degree the same. And if we say, okay, what else is missing? Well, the fact that this levels out and then goes up again, the short-term behavior behaves like the polynomial, right? That it around its root. And so if you just saw this, you would say that that has to be x cubed and not just x. X would be a straight line through it, right? X cubed levels out. And so that gives us the basis for putting a degree in here that's equal to the degree in the denominator. That makes that horizontal asymptote. Okay? All right, we have about 5 more minutes. I want to give you one out of the book that that looks different than the 2 or 3 that I've posted so far. Okay, so we've got kind of a crappy reproduction here. But this is, the root here is x equals 3 is one of the roots. The other one is x equals 2. And we have an asymptote at x equals 1. And we have the y-intercept f at 0 equals 2. Okay, see if you can put that together. Let me ask you a question first. This thing's going off to some place over here. This thing's going off to some place over there. It's going neither to 0 nor to an asymptote. What does that indicate?
1 over x.
I'm sorry?
1 over x.
Not 1 over x. No, that's what this thing indicates, is that you have some division that's going to cause a problem with your domain. The long-run behavior, if it goes off to something other than an asymptote, means that the degree in the numerator is higher than the degree in the denominator, right? Okay, so with that clue, why don't you try and put this together? Yes?
Does that mean this would be like a different asymptote, like oblique asymptote?
Yeah, now we're not going to cover that, but if it has a degree difference of 1, you will have an asymptote that's slanted, and we're going to ignore that. If you have a degree difference that's greater than that, then you don't really have a straight line asymptote. You only have a straight line when the degree is one higher than the other, and that's the oblique asymptote we're talking about. Yes?
Wait, what did you say about the long-term behavior? That was like a hidden question.
Yeah, the long-term behavior doesn't go off to some horizontal asymptote, whether y is 0 or y is some other value. So what that means is, since it goes off to some value towards infinity, that means that the degree of the numerator is higher than the degree of the denominator.